Hi, my name is Ankit Wagle. I am a PhD student at Arizona State University. I am here today to present a novel architecture for accelerating BNNs using a network of programmable threshold logic standard cells. I would like to thank NSF PFI for supporting this project. In a gist, this presentation will demonstrate how a highly efficient BNN accelerator is built using threshold logic cells or neuron cells. We will show that it is possible to achieve a 3x improvement in energy efficiency over an existing state-of-the-art architecture without sacrificing area, performance, or even accuracy. It should be noted that these improvements were achieved without using any of the standard low-power techniques such as voltage scaling or approximate computing. Before we deep dive into the architecture, it is necessary to understand what threshold functions are. Threshold functions are a subset of Boolean functions which are linearly separable. They are represented using the equation shown in this slide. As you can see, we first calculate the weighted sum of inputs. If this sum is greater than the threshold t, then the output is 1. Otherwise, it's 0. These functions can be easily implemented using the hardware neuron shown in this slide. There are 4 main components: the left and the right input network, the sense amplifier, and the latch. The left and the right input networks calculate the weighted sum and the threshold in the form of currents. The sense amplifier compares these currents from left and right input networks and performs the evaluation of the threshold function at the rising edge of the clock. Finally, the latch stores the result of the threshold function. In simplified terms, a neuron is equivalent to a flip-flop with embedded logic functionality. Note that a neuron is built using flash transistors, which are CMOS compatible. We will now show how a processing element is constructed. It's constructed using 4 neurons connected to each other. We call this processing element a TULIP-PE. Each neuron is also connected to a local register from which data can be accessed or written to. Using this arrangement, it is possible to implement several operations used in the BNNs, such as addition, comparison, batch normalization, max pooling, and ReLU. Although the details on how these operations are performed on the TULIP-PE can be found in the paper, we will show the flow used for executing these operations in the next slide. The nodes in a BNN are large threshold functions with typically 1,000 inputs or more. The flow shown on the slide helps to execute these BNN nodes on a TULIP-PE. First, each node is decomposed into a network of smaller threshold functions. Then, with appropriate inputs available to the P's, these threshold functions are scheduled on the neurons. All the intermediate data generated within the network are stored on the local registers. Finally, the result of the TULIP-PE is extracted through the output buffers. Now that we know how a BNN node is executed on a TULIP-PE, we can now look at how the top-level architecture operates. We built a single instruction multiple data architecture using the TULIP-PEs. The L1 and L2 image buffers are used to cache and broadcast image data to the P's. The kernel buffer provides the weights to the P's. We also have memory and processing unit controllers to help operate the architecture. We have additional MAC units within the architecture for handling layers with integer activations. Now, in order to evaluate this architecture, we chose another benchmark architecture by the name of Yoda. This architecture was chosen as it evaluates BNNs without using voltage scaling or approximate computing. We constructed both the Yoda-NN architecture and the TULIP architecture using TSMC 40 nanometer LP process. Both the architectures were evaluated by performing a 288 input neuron computation. It was seen that the TULIP-PE consumes about 60 times lower power as compared to the Mac unit. However, it is also 25 times slower than a Mac unit. Still, on the whole, the TULIP-PE has about 2.3x better energy delay product, while being 23 times smaller than the Mac unit. Although the processing elements show promising results, it is necessary to evaluate the top-level architecture to gauge the final benefits of using the TULIP-PE. We perform the evaluation using two neural networks. First is the binary net for CFAR10 image classification, and second is the AlexNet for ImageNet image classification. This table shows the comparison between Yoda-NN and TULIP architecture for convolution layers. It can be seen that the energy of TULIP is 3 times less than the energy required by Yoda-NN. Since the performance of both the architectures is about the same, the energy efficiency also improves by 3x. Then we extended this experiment to see how the two architectures perform when fully connected layers are included in the evaluation. When fully connected layers are implemented on both the architectures, most of the cycles and power is taken by the memory instead of the processing elements. Due to this, there is no difference between the energy and performance between the TULIP and Yoda-NN during the fully connected layers. Hence, the overall improvements in energy efficiency and even energy dilute from 3x to about 2.4x. Through this presentation, we showed that the TULIP architecture delivers better energy efficiency than the state-of-the-art architecture. This work can be further extended in multiple directions. First, we need to explore additional arrangements for the TULIP-PE that can help improve performance. Then, we need to see how the improvements can be boosted using voltage scaling and approximate computing. We should also explore alternate memory architectures that are used for data distribution of image and the kernels. Finally, we should explore various loop unrolling strategies that are used to improve the performance. Thank you.